Okay, good morning, everyone. Okay, first thing I have to say that this title might scare some people off, so my fault, I should have chosen a better title, but I hope that as I go along with the presentation, you can understand better what was doing here, and at least you're curious to pick up the paper on which this talk is based on. So, let's start. What are semantic relationships? Let's imagine that we have just this raw text, and we as humans, we can read it and we can understand it, what's going on here. We have a sentence about Noam Chomsky, about Buzz Aldrin, about Barack Obama, tells the places where they studied, where they lived. But for computers, this is just a bunch of strings and text. I mean, there's no information, like semantic information here for the computer, so we have to extract it piece by piece. And one of the first things that we can do is just apply a named entity recognizer, and we get all the person names, all the locations, and all the organizations. And now what we are interested to do is to see that for each pair of named entities, where they are related in a relation or not. And clearly we can see on the first one, between Noam Chomsky and East Oak Lane, it says that it was the place of birth of Noam Chomsky. On the second sentence, we can see that Buzz Aldrin studied at MIT, and so forth. So, semantic relationship extraction, just looking at these pairs of named entities and the textual context where they occur, and to infer whether a relationship is there or not. And let's imagine that now we had a perfect system that could extract all of them on this text, and we would have all these triples here that represent information. This is a bit more structured. It's not only text. There's some structure here. And the interesting things to do with these triples there is to index them in triple stores or knowledge graphs, and then we can use them for question answering. So for instance, now we can look at this graph and we can answer questions such as who studied in Cambridge located in Massachusetts, or which universities are located in Massachusetts. So basically this is what semantic relationships are and how we can use them, a use case, a typical use case of them. So this is going to be the basic outline of my presentation. I will just briefly go through approaches for semantic relationship extraction. Then I will focus on a method which is called semi-supervised or bootstrapping, depends on how you want to call it. Then I will present a system, Snowball, which is based on TF-IDF weighted vectors. And then I will present another system which has proposed, which is based on word embeddings, but follows basically the same architecture as Snowball. And at the end, I will just show the experimental evaluation on which I compared both systems. So this is kind of a taxonomy of the methods that you have for relationship extraction. There are two main, two main branches on extracting semantic relationships. You have the traditional one and you have the open one. The big difference is that the traditional one, you extract specified types of relationships instance, whether on the open information extraction, you just extract all possible relationships, whether they are valid or not, from a large collection of documents. And the open information extraction started something like 2007, 2008. The other methods already exist, the traditional since much longer time. So just going quickly through the different methods. Rule-based, you can think of it just basically like using regular expressions with lexicons, and you just build up rules to extract relationships. The good thing about this method is that with just the simple rules, you can extract lots of relationships, and typically they have a high precision, but a very low recall. And also the handmade rules are hard to maintain. If you want to update them and always go for more cases, at some point you see that's impossible to keep doing this job for a long time. Supervised learning, as all the goods and bads of supervised learning, you need training data, which it's not always easy to get, but then you can have all the fun or all the suffering with feature engineering and model tuning and all that cool stuff. Then we have bootstrapping, which I will go in more detail further ahead, but basically it takes advantage of unlabeled data, and also you need to handle with something called semantic drift, which I will explain also further ahead. There's yet another method called distantly supervised, on which basically it's a way to generate lots of training data for free. And how do you do that? Basically, it's just you go to a knowledge base like Wikipedia, and you can have a fact extracted there from the info box. For instance, that Berlin is the capital of Germany. And what you do then is that you go to a document collection, and for every sentence that you have Berlin and Germany, you assume that that sentence is holding a semantic relationship where it expresses that one entity is the capital of the other. Of course, that's not true for all sentences, so the biggest problem with this is how to filter those out. But it's also another way to get lots of training data for free. So, going now into more detail into the bootstrapping methods. So basically, this is the idea of bootstrapping. It has nothing to do with bootstrapping from statistics. Some people confuse it, but the idea is you just give what is called seeds, which basically is two named entities that have a relationship between them. For instance, Google and Mountain View, or SoundCloud and Berlin. Both of those seeds instances express the relationship of the headquarters of. For instance, Google is located in Mountain View, SoundCloud is in Berlin, and the idea is like, you will look for occurrences of those named entities in the text, and then the collection of documents. You will take the textual context where they occur, and you will use that textual context to extract more relationships of the same type. So the challenge here is how you can measure the similarity between the words like headquarter, HQ, and base campus, main offices, based in, made quarters in. So all those phrases, semantically, they are similar, and the idea of bootstrapping is to exploit that similarity to extract more relationships for free. So this is the typical architecture of a bootstrapping system. You have roughly 4 phases. You give as input the seed instances, and then what you have to do is to find for matches of those seed instances in the document collections, and you gather all the textual contexts where they occur. You will use those textual contexts to generate what's called extraction patterns. You can cluster them, and you can do many things with them, and you have patterns. Then you'll use those patterns to extract more relationships, and then at the end, you can add them to the seed set again and reiterate this process. In the last step, you have always to find a way to know if your system is going on the right direction or not, due to semantic drift, when things start to go a bit crazy. And that's why usually you also have to score the patterns of the instance. I will show that in more detail. So this was something that started, I believe, in the late 90s, and it started as a simple task of extracting relationships of a particular type, which will be ISA. And one of the things I remember reading in the papers that were published on that time was about finding biomedical categories for terms found in biomedical journals or papers in the late 90s. Then in the 2000s, some systems were proposed for extracting any type of relationship. One of the first ones was DIP, published in 1999. And actually, it's curious, Brin here is the co-founder of Google, so this paper in 1999 was published by him, and he was using the crawl of Google at the time to find author and book relationships. Like this book was published by this author. It was one of the first papers, and it's interesting to read if you are interested. The second one was Snowball, published in the early 2000s, and it would extract any kind of relationships based on TF-IDF weighted vector similarities. And then there was another one which is also very popular, published 2006, also to general relationship extraction, and it was based on point-wise mutual information. But now I will focus on Snowball, which was the one that I tried to improve. Okay, let's go deep into Snowball. Again, it uses the same architecture. I will try to go step by step and to explain how we handle each of these steps in detail. So the first step is to find the seed matches. So imagine that you give as a seed to the system SoundCloud and Berlin. So the system goes through all the sentences in the document collection, and imagine that he finds one sentence such as the tech company SoundCloud is based in Berlin, capital of Germany. So what you want to do is from this sentence, you want to capture first 3 contexts. The context of the words before the first entity, between the 2 entities, and after the last entity. And what the system does afterwards is to build a TF-IDF context, a vector for each of the contexts. And you will have something like this. You have 3 vectors. And every match of a seed instance will be represented by these tuples that you see down here, where you have one TF-IDF vector, the first named entity, another vector, the second entity, and the last vector. So in the first step, you just collect all the possible tuples with this form that you have. And then on the second step, you start to generate extraction patterns using these tuples. And the way the system does is with a very simple clustering algorithm. It's just a single pass clustering over all the collected tuples. How does this work? You have the first tuple, you put it in a single cluster alone. Then you take the second tuple, you compare it with the first. If the similarity is above a threshold, you keep it on that cluster. If not, you put it in a second cluster. And you do that for all the collected instances. The similarity metric to compare the tuples is based on a weight. It's based on the cosine similarity for each of the 3 contexts weighted by a value. It's the formula that you see up there. So it's basically the cosine similarity between the vectors. How do you generate extraction patterns? Then in each cluster, you have a bunch of tuples. You just average them. You average each context of them. So you average all the before contexts, all the between contexts, and the after contexts, and you have a single vector that represents an extraction pattern. So the next step is we want to match these extraction patterns with new stuff that we don't know. How do we do that? We know that we are extracting organization and locations relationships. So what we're going to do, we are going to extract every textual context where we have a named entity marked as an organization and close by another named entity marked as a location. Okay, one important thing I forgot to mention is the input for this system needs to have the named entities already recognized. That's crucial. You extract these contexts, you build the same vectors as I shown before, and then you compute the similarity to each of the extraction patterns that were built in the previous step. And then if the similarity is above a threshold tau sim, then you extract the instance. And what they're doing here, just thinking about these first 2 steps, like the find seed matches and generating the extraction patterns, we are just doing cosine similarities between TF-IDF weighted vectors. And there's a big limitation on doing this, which is, imagine that we have these 3 vectors: main headquarters in, is based in, and as offices in. And let's assume that, for instance, in is a stop word, so you just take it out. If you try to do the cosine similarity in between these vectors, it will always be 0 because they don't have any common words, any common dimensions. And this is the big limitation of the TF-IDF. So, of course, since 3-4 years ago, what you do, you use word embeddings. The main difference is now, before you had a vector that could represent a context. Now, for each word, you have a vector. And I thought at the time, okay, let's try to plug in this distributional semantics, the word vectors, into Snowball. And I want to keep the same architecture. I want to keep things simple. I don't want to change much. So now I have the problem of how to transform several words on which each word has a vector into a single vector, so that the architecture of the system still holds. And I will go now with the bread systems explaining. So it has the same architecture as Snowball. The first step is find the seed matches, and the breads will do it in a different way. So we do the same thing. Imagine that we give SoundCloud and Berlin. We look for the same for all the sentences in the document collection where they both occur. Imagine that we found this one. SoundCloud online audio platform is based in Berlin, Germany. So what we want to do now, we don't. If we're going to use embeddings, each word here is going to be a vector, and probably there are words here that are not important for the relationship. I mean, online audio platform doesn't give you much. It says what the company does, but it's not important to know that it's located in Berlin. So what I thought about was to use some patterns that are from another system, a system called Reverb, which does open information extraction. And basically, it restricts a relationship between two named entities to be a verb followed by a preposition, or a verb followed by nouns, adjectives, adverbs, and ending in a preposition. So if we try to apply this pattern to these sentences, looking for the text between SoundCloud and Berlin, what we get is we select just these words. And this is perfect. So now the other ones we can discard, and we are just going to use these three words, is based in. A problem with this method is, okay, of course, first you need to pass a tagger on your text, and you have the part of speech tags. And then is that we are restricting a relationship to be mediated by a verb. On the pattern, you always find a verb. You always need a verb there. So, but there are also relationships, for instance, this one, that says that this guy is the CEO of that company, that doesn't have any verb, but you have a relationship there. I mean, simple solution here, what I do, I just take all of the text. So, and now the problem is each of these words marked in bold is a vector, and we want to average them or do some other compositionality function just to have one single vector. And what I do is something also very simple. I just remove every word which is part of a stop words list and every word which is marked as an adjective. And then at the end, I just sum the embeddings of each word. So we had these tuples that were extracted before. Now we're going to remove stop words and adjectives. We get something like this. And now we're just going to use the embeddings. In this case, it's even perfect. This was hand-picked examples, okay? But you get just one word on the between context. You get two on the after context for the second sentence, but you just need to sum them. And yeah, okay, this is clean. And now you just need to sum them. And you have, again, the same tuples that you had before on the original snowball system. Now we are going to the second phase. Like just showing back, we were on the first one, find seed matches. Now we're going to the second one, generate extraction patterns. So we have these tuples, we want to cluster them. The cluster will be done in the same way, as I explained before, using also the same similarity metric. The problem here is, it's not actually a problem. Well, it was a problem when I did the experiments, but what happened is that at the end we have several tuples in each of the clusters. And I already was summing or averaging the word embeddings of each word. And now I wanted I want the cluster to be represented by a single vector, like it was on the original snowball. But what I found in this experience is that if I would now start to average the sum of the word embeddings, the semantics were starting to get lost, and these things will get out of control. So I understood that I have to keep the embeddings like they are. I cannot average them because the results are much better. So I just change the similarity function. And the way that is defined is the similarity between an instance and the cluster, where in the cluster you have lots of instances, is the maximum of all the similarities between any of the instances in the cluster. So you're going to take your tuple extract before, and you're going to compute the similarity with all the instances in the cluster. And if the majority of the similarities is higher than the threshold, you say that the similarity to that cluster is the maximum of the similarities. And I defined the new similarity function on the bread systems like this, and I kept it through all the pipeline. And those were basically the two biggest plugins that I changed on the original system. I wanted to keep the rest of the architecture as the same, to keep things simple. Didn't want to try out many different things. So we already went to the first one, find the seed matches, generate extraction patterns. Now let's find the relationship instances. It's the same thing as before. We just extract the context, but now when we apply the similarity metric, we are doing actually over word embeddings and not over TF-IDF weighted vectors. So again, we look for contexts, we extract the textual context, we build the vectors as before, and then if the similarity with extraction patterns is above threshold tau-sim, we extract it. And then here we start to taking care of what is called semantic drift. So what we do is we have a formula to update the confidence of a scoring pattern, which I will describe in the next slide. So imagine that we found a new instance on the text, and we are going to extract that instance because the similarity with the extraction patterns says so, that we should extract it. And imagine that we gave as input on the initial seed set SoundCloud and Berlin. If the extracted instance is also SoundCloud and Berlin, then we give a positive point to the pattern because it extracted something that we already know. If, for instance, the extraction patterns extract something like SoundCloud and London, for instance, then you give a negative point because it doesn't correspond to what's on the initial seed set. If it's unknown, if it's something that we don't know, we just give an unknown point. And then at the end, we compute the confidence of the pattern using the formula above. Another important thing is that for each extracted instance that we can take from the document collection, we keep track of the patterns that extracted it and what was the similarity score. This is used ahead to compute the semantic drift. So we are going now to explain how to handle with the semantic drift. So what is the semantic drift? The semantic drift happens when the new relationship instance that are being extracted or where the seed occurs, but they have a different semantics than the seed set. For instance, if you have Google Mountain View as a seed, we can extract Google and headquarters in Mountain View. It's okay. We want to start the locations of companies. Google based in Mountain View is also okay. But the system might match something like Google shareholders meetings in Mountain View. And this doesn't hold that Google's locations in Mountain View. Or, I mean, for me, it doesn't. So this can generate extraction patterns that will start to target other relationships types. And this starts to propagate to the bootstrapping iterations of the system. And this just starts to drift away from the original thing. So on the few slides before, I told that for each instance that you extract, you keep track of which patterns extracted it and what was the similarity score. So at the end, you're just going to apply this formula, which is just a weighted measure between the confidence of the pattern and the similarity that that pattern had with the instance to score the instances. So every instance extracted by the system will have a score. And at the end, what you do before adding the seed instances to the seed set, you just take the top k. You set another threshold called tau min, and you say everything above this threshold goes to the seed set. Everything that's below, you just discard it. And it's finished. This is how the system works. So on the first, you find the seed matches, you find the contexts, you cluster them, you have extraction patterns, use the extraction patterns to find new relationship instances, and you rank the patterns. And then in the last step, you will rank the instances, and then you take just a few instances to the seed set again, and you repeat this process until to a fixed number of iterations. You can put 4, 5, 6, depending on the size of your document collection. So I now go explain how I evaluated these two systems. So the first thing to do was to find a document collection where I could put the two systems at work. So I took English new articles from the GigaWord collection, which basically contains 5.5 million new articles published between 1994 and 2010. I did the pre-processing of that document collection, did sentence detection and word tokenization part of speech tagging with the Python NLTK, and then I used the Stanford-NAIR to tag the named entities. Also over this collection, I generated word embeddings using the skipgram with legend 5 and vectors of dimension 200. And then what I did over these sentences was I look at these sentences, let's just keep the ones that have at least 2 entities and those entities are mentioned on Freebase. And at the end, I had a data set with 1.2 million sentences. And this was the document collection to evaluate both systems, to compare the systems. What was done before? So I had Breads, which I implemented the system. I also implemented Snowball using the TF-IDF, but with a slightly change on which the words for the between context were being selected, and then also the original snowball, the classic one. And then I played around with lots of parameters. So for the tau sim and the tau min, I varied those parameters between 0.5 and 1.10. Also for the similarity measure, you always have to weight the contexts. I basically played around with two schemas. One which just considers the between context, and then the second one which also considers the before and the after context, but with a lower 8. And I did the experiments for 4 types of relationships. Acquired means like one company acquired the other. Founders, like who was the founder of which company. The headquarters, where does each company has the headquarters, and the affiliation, which people work for which company. And okay, I left this just running on the machine for 1 week almost, and then at the end you just collect the results, you compare them, and okay, this is lots of information, I'll just go quickly. So basically here on the first column, just have the number of instances extracted by each system. You can see that Breads extract much more special for the affiliation relationship, and also with a good precision and recall. It beat all the other systems. I mean, I saw this, I was happy, and then I started understanding why. I wanted to see more of the results. And basically what happens, as I was expected, is due to the way that the embeddings work. When you try to find similarities between the words, you can expand it to more words. For instance, Breads could expand the vocabulary for the acquired relationships to acquired, acquisition, purchased by, /s, purchase of the founders. They also expanded, and special affiliation. These are just the top words used that the system used to extract relationships. But you can see clearly that given just 2 seeds, so for every relationship I only gave 2 seeds, and based on those 2 seeds, especially for the affiliation, I could get much more related words that co-occur with those. And the other systems, due to being based on TF-IDF, they just got stuck on those simple words. Nevertheless, there is still some improvements that can be done on Breads. So the thing is, I'm using part of speech tags just to find the relationships between 2 entities, or the words that mediate. And most of the times, or for almost, half of the times, that's not enough, depending on how the relationship expressed in the sentence. For instance, the International Court of Justice, which is part of the United Nations, is based in The Hague. If we are going to look for the relationship between the United Nations and The Hague, what we have is the United Nations is based in The Hague, which is wrong. This is not what the sentence is saying. This is totally wrong. This is because of using only part of speech taggings. And these kind of errors can only be alleviated if you go to syntactic dependencies. If we try to understand what are the relationships between the words, not what is the function of the word in the sentence, but how are the words connected to each other. And if you look here, the word based connects The Hague with the International Court of Justice, which is what the sentence is saying. The International Court of Justice is based in The Hague. Another improvement that I could do is, instead of using only named entity recognizers, which is just a surface string. It just tags the string as being a person, or location, or organization, will be to pre-process the document collection with something called entity linking, on which, when you see George Bush, the system could tell based on the context if that entity name George Bush is George Bush the father or George Bush the son. Or whether if you just see the word Bush, is George Bush the father, the son, if it's the band Bush, or if it's a company called Bush. I mean, the main advantage of this is that then you can, instead of giving then string names, you have to give identifiers to entities, but you have much more contexts where those entities occur, because the same entity can be mentioned by different surface strings, and the system was then already aware of this. And and that's it. You have I have both of the systems implemented on the GitHub, and I also have the paper where I can explain much more in detail how the system works. And I hope at least I can convince you to go and read the paper.
questions?
On the slide, evaluation, seeds and systems. The next one.
This one.
Yeah, how did you decide on the context weighting, the alpha, beta, and gamma? Did you do some kind of optimization to find which one was the best, or did you just randomly pick?
No. What I did was I had the feeling that in the between context it was where the relation was expressed, but I also wanted to explore the other ones. I just say, okay, let's put it like this. Okay, one other thing is that I could do. A third one was to give 1/3 of 8 to each of the contexts and see which one occurs. But I mean, especially if you're only using part of speech tags to extract relationships, I would say that most of the times the words that mediate the relationship are in the between context.
Okay, so you just picked these weights and saw, okay, they're optimal. Did you try different ones?
No, I didn't.
Okay.
I didn't. It was like this.
Okay.
I didn't. Yeah.
All right,
no.
thanks.
Thank you for your talk. I was wondering, what is the or what are the bottlenecks of this algorithm? Because you said it was running for a week. Why? Like,
the bottlenecks.
Yeah.
Okay, there's those two that I referred, using only the part of speech tags, and there's another big one which is related. I didn't put it on the slides actually, but I know when I was working with it, which is where is it? It's here. This is not so easy to understand, but you see how the way that you are ranking patterns limits away. For instance, in this case, you are extracting, if you extract relationships, for instance, like Google headquarters. Basically, every company only has one headquarters, but you can have relationships that are not unique. Let me think about, I don't know. Imagine that it's not the headquarters of companies, but installations or settlements of companies. Some companies can have offices all over the world. What happens here, imagine that SoundCloud, for instance, which was one of the seeds, had that. If you extract something from the text, like SoundCloud also has offices in Berlin, but you didn't give it as a seed, the pattern will be ranked wrongly. But that will not be correct, because you also want that. So what we want is the way that this formula here is used to rank patterns needs to be changed, because this is a limitation, this is a weakness here. I don't know if it was clear, if you understand with the example. I can explain to you offline, I can show you, yeah, but I know that here was another one of the weakest of the system.
Yeah, I have a question about how can time be built into these models? For example, relationships can change over time. For example, you said, and even there might be even other problems, like this George Bush problem,
yeah.
that in like year 2000, probably George Bush, it depends on the year of the, for example, of the news article, which person it might refer to, or affiliations might change over time.
Yeah, okay. One thing is you just want to extract what's correct based on the documents. The documents, it's a collection of news articles from 94 to 2010. So what's written there, let's assume it's valid for that time period. There's nothing else that you can do. One thing that I find interesting was when I was evaluating these relationships, I did a bigger experience for this. This is on the paper, but on my thesis, there's one chapter where I did much more experiences, and I was extracting a relationship was who is the president or the CEO of companies and or organizations, and one of the stuff that it extracted from these documents from 94 to 2010 was one document from 2007 or 8 on which the president of FIFA was one guy. But then when I compared with the information on Freebase to validate the relationships, Freebase was more actual and the president had changed. So actually, he extracted the correct relationship from a document, but the evaluation said it was wrong because that information was up until 2010 and Freebase was a knowledge base updated like, yearly or something like that. That was, I mean, but the main goal of the system, you just extract what's on the document. You don't, to validate whether that in the real life is valid or not, that's another problem. You just want to extract what is being said on the document.
Thank you for your talk. How does the system deals with the fact that two people can have the same name but actually do something different? For example, like Michael Jordan is a basketball player, but there's also Michael Jordan, the researcher.
Yeah. I mean, it doesn't. That's why I put the. It doesn't deal with that. That's why I put, instead of using simply named entity recognition, let's pre-process the document collection with an entity linking system. And then instead of giving just Michael Jordan and the team to which it plays, you give the IDs of each of the entities. And the text should know that those IDs correspond. No.
Hello. Great talk. I really enjoyed. I had like two little questions. One is the way you define similarity. That's like it's not normalized. Like it could. And you put like in the snowball part,
yeah.
The way you do it, like it may be difficult to compare different things with that similarity. I think it's the cap is not. I think is it possible you may need to normalize it to be able to compare it with other similarities? That's one thing, and the other thing is the way you chose the thresholds for the keeping the relationships.
Yeah, okay. The similarities, I didn't normalize them. I just used the vectors as they are. So, I mean, I don't know how big of an influence it could be to normalize them, but I didn't in the experiments. For the thresholds, what I did, so basically you have here thresholds, tau sim, tau min. What I did was I explored on the system all the combinations of them. So tau sim equals to 0.5 and then tau min equals to 0.5, 6, 7, 8, 9. So I use this, so it's like 6 times 6 possible values, then times 2 awaiting configurations, then times 4 relationships. This was not clear on the system, but I left this running on the server for almost like 1 week, doing all this in parallel. It took so, but yeah, I mean, I didn't explore threshold values below 0.5. I mean, I don't think that will make much sense. I just started from 0.5 up to 1.0. Yeah.
Yeah, maybe another question. So you added this new similarity where you don't use the average vectors, but like the max, best fitting one.
Yeah.
Have you tried, like, if you use this approach with normal TF-IDF vectors, does it improve as well?
A good question. It might. I don't know. Good, but yeah, a good question. I don't know. I think when you average stuff and you average over average, you start to lose semantics of stuff. Yeah, yeah.
Thank you. If no other question, then let's thank David again for his wonderful talk.
Thanks.